Hi, everyone. Today I want to talk about high-performance message dispatch. But before I do, I want to introduce myself a little bit. I am a power management firmware architect at Intel, and I've been writing C++ only for about 4 years or so, but it really has me hooked. I enjoy it quite a bit. I'm the maintainer of the CIB library up on the Intel GitHub for composing modular firmware. And I'm also the creator of the tiny FPGA development boards, if you've seen those. So this high-performance message dispatch algorithm is something that we're working on at the moment, actually, and there's a pull request up on our GitHub for it. The initial results are really quite good. We've benchmarked this using a 400 megahertz ARC HS CPU. It's not commonly used in dev boards for makers, but it's very commonly used as a IP from Synopsys. But with this processor, we're able to get 100 to 200 nanoseconds latency for message dispatch. And I've said message dispatch a whole bunch of times now. What does that mean exactly? Well, in any embedded system, we have interfaces where we talk to other components either on the chip or off the chip. And so we can receive messages or packets or transactions, however we might want to call it. And that message, when we receive it, needs to be decoded. And once we know what it is, we have to figure out, okay, which part of our firmware application wants to handle this message, right? Ideally, we have a modular construction where different components can register to process certain messages. And that's what we have today in the CIB library. We have this message handler service that can allow you to register callbacks for these message types. But we have challenges. We have relatively constrained processing power and memory. And many times when you're developing a full custom ASIC and you have a microprocessor in there, that microprocessor is actually taking over tasks that used to be done by hardware. And so there was a certain expectation on how quickly the hardware could process these events that then goes on to the firmware to be able to process them very quickly as well. And this is really because we have real-time processing requirements. We need to get our things done. We need to respond to these events. Otherwise, we're going to have skipped audio, which sounds very bad. We're going to have skipped frames in video, or we're going to have other issues that degrade the quality of service. Furthermore, our hardware lives out in the market for a very long time. And so we may have to maintain that firmware along with the hardware and send patches and updates. So we could be supporting multiple years worth of products at any given time while we're working on several years worth of new products. There's a few things that we have tried to really embrace when we develop our firmware in our group here at Intel. And we want to make sure, number one, that our firmware is composable. And what that means is we can create independent components by independent team members or teams, and then we can pick and choose for a product which features do we need, which features do we have to have for that product, and then compose them together. And composing should be you add it to a list or you don't add it to the list. That's true composition. If there's a bunch of extra work that you have to do after the fact, that's not really scalable. That's not really composition. That's just something that looks nice in one area and you have a big mess in the back end. In order for these components to be composed together, they actually have to be decoupled. We shouldn't have any false dependencies from one component to another. Any dependency should be because, well, of course I need to talk to a web host over Ethernet, right? So I'm going to have a dependency on Ethernet and probably TCP/IP or Wi-Fi, right? So we want to remove these interrelationships if they aren't absolutely necessary. And if we do have a dependency, the dependency should be on the interface and not the implementation. So yes, composability requires decoupling of our components. And we do this with clean interfaces. We also need to do this with independent performance. It's not just our interfaces that need to be clean to enable composition. We have to have independent performance. Obviously, there are certain things that aren't going to allow us to do that. If we have a very, very processor-intensive task that just requires a lot of time to do its job, then of course it's going to alter the performance of the system as a whole. But if we have a lot of independent components and each one really isn't consuming a lot of processor time, they should be independent. For clean interfaces, we use the CIB library. A CIB stands for compile time, initialization, and build. I'm an engineer, not a marketer, so we have a very terrible name for it. But it allows us to have this registration system at compile time. So all of our components, their features can say, hey, whenever I receive this message type, or whenever I receive a message that matches this predicate, I want my callback to be executed. And all of our components can register for this. And it happens at compile time. So I don't spend any runtime initialization setting up lists and setting up data structures and things like that. All of that is baked in at compile time and then often loaded using a simple memcopy when we boot. Part of the CIB library is this message handling service. We have much more than that, but this is the part that we're going to talk about today. So the first step is we need to be able to define our messages. And we do this in a declarative way. So we don't have functions that say what it needs to be. We don't even use regular structs, which would also be declarative. But we want to define it in a way that the rest of our framework can understand it. It can extract the fields. And we can give these compile time string names. So we actually get very efficient two-string functions for our messages that don't require runtime processing. When we receive a message, our application code and our components can create a callback. And this callback has a few parts to it. First, it has a name. The name is really good for debug and logging. But the interesting part of the functionality is this callback predicate. And again, this predicate is written in a way that the message handling library can understand it. It understands what are the requirements for a message to match. And it doesn't force you to say, oh, you must match on this opcode first, and then everything else is handled in a different way. It's really all a uniform mechanism. And finally, we pass in a lambda for our callback action. And so the framework behind the scenes actually takes the raw data and it effectively casts it into the correct message type. And it checks the predicate to make sure that it matches before it calls your action. So at this point, you don't need to know what interface this came from necessarily. You don't need to know the details of the hardware. You just know I created this callback. This is the entry point for my processing. And then we can take these callbacks and we can define a component. A component is, in CIB, basically a struct that has this config parameter. And this config parameter says, I want to extend the controller bus message service with these two callbacks. And we have another one for our power controller. At our top level, this is the part where the composition really takes place. We can basically say, this is our list of components that I want for this project. And it'll go through, take in these components. At any level, we can also export various services. So in this case, I'm exporting it at the top because this is slideware. But the CIB library then takes these components, does all the calculations at compile time, and enables the system to run right out of the bat at runtime. So we have a clean interface. That's how the CIB library works today. The other part of the equation is independent performance. And so the addition or removal of components shouldn't have a huge impact on our performance. It should be predictable. We should know, effectively what should happen. We should be able to scale up to more components. We should be able to add additional callbacks without paying a hefty price. The CIB library enables composition and performance by offloading these calculations at compile time. It's not just registering some callback that gets executed later. There's actually a lot of computation that can happen to simplify things and to enable even higher levels of abstraction. One of those libraries in CIB is the flow library that allows us to create dependencies between callbacks. And so we can actually register things independently, but say, this action needs to execute after action A, but before action C. With the message library, we have a lot of very interesting opportunities to take all of this information, including the type information at compile time, and use that to create an optimized algorithm and an optimized solution specific to your needs. So this is the benchmark for our old algorithm and our new algorithm. The blue line is a naive predicate evaluation. And what this does is it iterates over the list of callbacks and it evaluates the predicates one by one. For any predicates that match, it then executes that callback. The horizontal axis here is basically our new algorithm. I chose not to do a logarithmic scale because this illustrates the performance difference better, actually. In fact, the new dispatch algorithm in my benchmarks of up to 155 callbacks never exceeds 145 nanoseconds dispatch time. This is the point where we pass the message to the service until the service determines what callback this goes to and actually executes that function. And in this case, it also does a small, that function writes to a volatile variable so it doesn't get optimized out. By the way, for these benchmarks and for all of the work that we do at Intel, in my firmware team, we always use 03 for everything. I did this benchmark yesterday, and to be honest, I can't explain this. I don't know why it got better. It's quite unpredictable. I do suspect that this huge increase is due to instruction cache pressure as well as branch predictor pressure. But that'll require some further investigation. How do we do this? How do we achieve this performance improvement? Because this is a huge difference. Well, we actually take a page from database design and database implementations. And what we do is for a set of fields that you've identified as really important, things like command, opcode, source address, destination address, things like that, we can generate fast lookup indices. And so each one of these indices will map a particular field and value to a set of callbacks that match that requirement. And then across these different lookups, we can take the set intersection of all of these and find which callbacks match all of these field values. And because we're using the CIB framework, we can do all of this at compile time. So here's an example. We have a very basic motor or movement control system, and we're receiving some messages on this system. And we have a table of these callbacks. Each row is a different callback, and each column is a different field type: opcode, sub-opcode, and source ID. So here we can see this is basically how we might decode these messages and determine which callback they go to. So first we get a move command. And so our algorithm goes through and finds these are all of the messages that match that move field, that opcode field. And then for sub-opcode, we have forward. So again, we go and we find all of the callbacks that match that requirement. And you notice these entries that have a dash, that means there was no requirement. So it'll match any value. And finally, for our source ID, we have, this is coming from a user. It's an unprivileged access. And so we match almost everything. And at the end, we go through and we find the set intersection of these. We find that the move forward callback matches this, and the log movement callback matches this as well. And so we've actually enabled movement processing and a logging process to log which commands we've received without any interaction between these two components. Looking at it another way, this is the basic runtime algorithm. We get our message coming in, we extract the indexed fields, we pass them through our lookups. In this case, we have 3 different lookups. From the results, we calculate the set intersection. We figure out which callbacks match all of these. Then we iterate over those, and we actually invoke each of those callbacks. So we're going to look at this algorithm one piece at a time. The first part, and actually really performance sensitive part, is how do we do this lookup in the first place? We really want an efficient way to do this. We don't want this to be slower than a linear search. Strangely enough, one of the lookup algorithms is a linear search. Linear search is maybe seen as slow algorithmically. It's big O of n, so worst case, you have to iterate over everything. But this can be done with a very small coefficient. And so depending on the number of elements that you need to search through, it can actually be the most efficient algorithm to use. And because we're building all of this at compile time, we know how many elements we have. And so we can actually pick at compile time, this is the right algorithm to use because we have 4 elements, and we can do this lookup very, very quickly. In fact, on the ARC processor, this is a dual issue processor. It has predicated execution of most of its instructions. We can actually do that search in 1 cycle per element. So it's very, very fast. Another interesting thing about the ARC processor, number 1, dual issue. It does have a 10-stage pipeline, so we need branch prediction. So we have to be sensitive to that. This means there are certain cases where we want to use conditional moves or conditional execution rather than branches. But it also has 2 ALUs in each pipeline, as an early ALU and a late ALU. And this is interesting because the early ALU can help generate addresses before we do a memory access. The late ALU can immediately process the result of a memory read. And so all of this stuff is important to me, not because I have a particular project that I need to implement and I'm using this and I want to know these details, but from the other perspective, as a library developer, I can pick strategies that are tuned to this architecture. So I can pick strategies that will be fast for this, and on other CPUs, I can have other strategies that work well for those architectures. All of our benchmarks for this presentation were executed on real hardware, on this actual dev board, which has an ARC HS4X, lots of RAM that I don't use, cache as well, which I prefer not to have for simplicity and predictability. So benchmarking this linear search, you notice at 0, well, it should be very fast at 0 elements. 1, 2, 4, and so on, it's a perfect linear scaling as we expected. So this is a good sanity check. And if we only have 1 element, we actually have a 10 nanosecond access. If we have 2, it goes up by 1 cycle, actually 2.5 nanoseconds, and so on and so forth. So for very small numbers of entries, this is quite useful. Another strategy that can be easily overlooked when you're looking at binary search trees and you're looking at hash maps is a direct array lookup. And direct array lookup can be extremely useful when your key space is very dense. It's very close together. So you don't have a lot of gaps in between your keys. And this is interesting because that density can actually be a lot more sparse than you'd think. When you move to use an actual hash map, hashes are never 100% allocated. Almost never, anyway. There's one specific algorithm that can do that. I'll talk about that later. But usually your load factor is somewhere around 50% to 75%. That means you're not using 50 to 25% of your storage in the first place. Depending on your key space, a direct array lookup could actually use less storage than a hash, and it's going to be a lot faster. It's an excellent strategy to use, and the code for it is quite simple, and the benchmark is also very simple. These are in nanoseconds. These are nano benchmarks, so there's some noise in it. The branch for the loop and incrementing the branch variable actually adds some noise here, but this is extremely consistent across the board. The last algorithm that I want to look at that's very useful for what we want to do here is a hash lookup. And a hash lookup is also quite efficient. Not as efficient as a direct array lookup because we have a hash function that we need to execute, and this is going to take some cycles. Nice thing about the hash lookup is your function doesn't have to be perfect. You can bound a linear probing strategy, so you can check one or two additional buckets depending on how sensitive you are to storage, so you can have a higher load factor. And the runtime's constant, and it's really quite nice, and it works very well for sparse key space. So once your keys are further apart, when you have like a small opcode field, for example, your commands will typically be very close. Maybe you have some sort of addressing scheme where your values are going to be further apart. Very interesting graph. I probably should have made this a bar graph in hindsight. But regardless of the number of elements, and I'm going to 14 here, but this goes on to whatever your memory limit is, assuming a cache-less architecture. It's effectively constant. But you notice I have several different strategies here. And the reason why I have several different strategies is because some hash functions are really awful, but they're very cheap. And they might happen to work for your specific set of keys. And that's very useful. The more expensive ones are really good, but they take longer, and we don't want to use them if we don't have to. So we can build a composite lookup strategy. We can have multiple different algorithms that we can pick from, and we can sort them based on their performance, and we can basically have a list of these strategies at compile time. And so for the Arc CPU, the one that we have, I have a list that looks something like this. If it's a small enough number of elements, then I want to use a linear search lookup because that's extremely fast. If it has a dense enough key space, I definitely want to go with a direct array lookup because that's the next fastest thing I can do. Else, I'm probably going to end up using a hash lookup. And this first parameter is the load factor that I'm aiming for. The second parameter is how many additional entries I want to search. And these are the hash functions. These are the awful ones that are very fast. When we combine multiple strategies, we can get something like the yellow line here at the bottom, where we are always picking the most optimal strategy. And then depending on the density of the keys, we might not be able to do array lookup, but this hash function might work, etc. And so we're always trying to get the best performance in our lookup algorithms. These hash functions were generated by an algorithm, basically literally trying random combinations of things and random coefficients. There's a project called Hash Prospector that I adapted for this. It's really cool. If you're interested, I advise checking it out. So we have a fast lookup. Now we need to take these sets of callbacks and process them in an efficient way. We have to find what is the set intersection. That sounds complicated. It sounds slow. it's really not too bad because we can just represent the set of callbacks as a bit mask. Each bit index represents a callback index. So we have a very dense representation, but we can also find a set intersection with a bitwise AND, which is very fast. And so we can very quickly find which callbacks match all of the fields in that message. There is a downside to this in terms of our storage size. It doesn't scale very well, but we have future plans to basically use run length encoding to compress these bitmask fields. And that should have a pretty significant space savings, and it actually scales a bit better than using the bitmasks themselves. And finally, we have our set of matching callbacks, and we need to execute them. We have a bitmask. We have to figure out which bits in each 32-bit word are set. C++20 has a really useful header called bits, and we can use the count reverse zero. So that counts the number of zeros until the first set bit, and then we can clear that bit, find the next one, clear it, find the next one, and we just iterate until we're gone through the entire mask and executed all of the callbacks. And finally, we have our user application callbacks, which the library itself doesn't care too much about. It doesn't do much with except actually invoke them. So in the beginning, with this CIB library and the message handler, we developed a very clean interface that gives us a lot of power and control over exactly how our callbacks process different messages. Because that interface was declarative, it enables the library itself to extract that information. The interface doesn't say how to do things. It just says, what is it that I want from the library? That interface enabled us to create this high performance version of our message service where we can do this dispatch extremely fast and predictably, right? We're always hugging that horizontal axis. Additionally, we have this nice lookup library, which is independent of the dispatch library that we can reuse for many other things. And it will always figure out what's the fastest algorithm to use for your architecture. Well, for your architecture, assuming somebody has created a set of strategies for your architecture. But at that point, it can be reused for many other things. All of this work is online at the Intel CIB GitHub project page. You can look at it right now if you want. It's in progress. There's a lot of ugly things, so if you want to comment and find some awful things in my code, please go ahead. I love feedback. Might be entertaining. We'll see. There's still some work to be done. The run length encoding of the bit masks, for example. Right now, I'm punting on the predicate processing. I expect the predicates to be specified in a certain way. Really, though, you should be able to define any sort of Boolean formula, and it will be able to simplify it to a correct product of sums and extract the information. I'm also using a different callback interface from the normal one that needs to be consolidated and made the same. This should be a drop-in replacement for the existing strategy. And some logging and other cleanup and bug fixes, I'm sure. So thank you, everyone, for coming to my talk.
I'll go around.
Yes, thank you very much for the talk. I've got two questions. First question would be, how is there a concept to handle different priorities of callbacks? And the second question would be, since those callbacks are user-defined, they can get pretty long in some cases. So is there, what concept of interrupting a callback to execute a let's say, higher priority function do you have, or
Okay.
is there any plan?
Okay, yeah, that's an excellent question. We have a scheduling library that we use internally. It's kind of specific to the hardware that we have, so we haven't open sourced it yet, but at some point we should be able to do that. The way that we do this is any messaging interface, we basically put that on the highest priority interrupt. Because when we get a message, we don't know what it is yet. We don't know if we need to handle this right away or if we can take our time in processing it. We get the message, it's decoded at the highest interrupt context. We actually have 16 different priority levels that are all nestable and preemptible. And so our interrupts and our scheduler tasks are really the same thing. There's no difference. We do all of our execution in interrupt context, which is good in this case and not bad. After we decode the message and it gets sent to the callback can then schedule itself to execute and process that message at the appropriate priority level. And the really important part of the priority levels is we implement rate monotonic scheduling. So the priority level that we schedule it at is proportional to how quickly we have to respond to it. And if we do that, our scheduling can also be determined independently, and it can be decoupled across our tasks.
Thank you for your talk. I have two questions, and the first one would be, you mentioned that you don't use the cache. What impact would that have if you use it? And the second one, you also had a point that there was this could also be used in other things than embedded. Could you provide an example for that? Thank you.
Oh, okay. Well, we can go back to this graph. For my benchmarks, I am using the cache. I don't. For my applications, a cache adds complexity. It adds a power cost, and then I still need to have my main memory somewhere, right? So I'm able to get by without having a cache, and I can have large enough SRAMs for our purposes. But the cache doesn't hurt this algorithm. It's perfectly fine with the cache on the dev board. Real world applications outside of embedded. I keep thinking in my mind something like an event bus, which is a common pattern in some applications where you have a common event bus and you can post events, and then depending on the attributes of that event, it can get processed by different parts of your application. I think there's other things, but I'm not creative enough or imaginative enough right now. Yeah. Yeah. Yep. Yeah. I thought about using a CAN bus example, but I don't know anything about CAN bus. Yep. Yeah. There's a possibility to do that. Yeah. But right now it's decoupled. Maybe in the future we'll have a improvement to that.
So you're doing an optimization at compile time. What's the compile time impact of that to select the correct algorithm?
It's better than I expected. I was very worried that this would have much worse performance, but actually the compile time for this one is proportional to its runtime. So the naive algorithm was actually much slower compile time, which was interesting to me. So that's another thing for me to investigate, at least on GCC 12. That's the case. The compile time for this algorithm, regardless of the number of callbacks, was seconds. This one could take up to a minute. Yeah, that was a happy surprise.
Very interesting. And you prioritize the consistent runtime over getting better runtime in some cases. Correct?
I optimized for absolute performance and like worst case execution time. And it was a happy accident that it was very consistent.
But I would assume that there are messages that are occurring much more often than other messages.
Yeah.
So to optimize for them, you would make a different algorithm and say, okay, if it's always message 1, then that's what we always do. So you have a direct comparison done, or basically also in the if-else branches, you want to set that at the top and do a jump because it occurs all the time.
Yeah, that could save, a few nanoseconds for a very small set of messages. But then that amount of time that you save, you're also adding additional time to the rest of the messages that you need to handle. So I preferred handling everything very quickly.
Right. Another question. You looked into the different strategies for the lookup. Have you investigated compile time generation of perfect hash functions for this?
Yes. So there's the frozen library. And the frozen library is quite nice. This line up here uses the frozen library and its perfect hash function. The downside of the perfect hash algorithms is you typically need to do 2 hash lookups. So you execute the hash function once, you look up into an intermediate table, and this intermediate table has additional parameter to feed into the hash function again for the final table.
And that looks more like a sparse set or sparse map than to me.
It's the final array of the data has no gaps in it.
Okay.
Yeah.
Is this a property you need, that there are no gaps in the final data?
No.
Because then you might still get a boost out of a perfect hash function instead of using these very fast but not very good hash functions.
I see. Yeah. So a perfect hash. Okay. So frozen is a minimal perfect hash, which is why it has that intermediate table, so it can pack everything. I actually evaluate a lot of hash functions, and the better hash functions are longer, bigger multiplies, a larger coefficient for the multiplication, which actually affects your performance because it takes, more instructions to load that coefficient, right? A very small and crummy hash function, if you only have to do one additional probe, that one additional probe is fast, right? So even though you're probing one additional location every single time, it's still faster than the longer but better hash function.
Okay, thank you.
Yeah.
Any other questions? Yeah.
Another idea spontaneously might be garbage. Did you look into trimming your columns, basically? So if there's only one message left, you might be better not to do another lookup with all possible messages and instead skip it and postpone or delay the comparison into the wrapper of the callback or something like that. So
yeah. So for indexed fields, we're always going to have this index, and you kind of have to pick that manually right now. You have to decide which fields to create indexes for. The fields that are not indexed are going to be checked within the callback, and that can be done automatically by the library. So the library, when it's done, will take out the indexed fields from the predicate, put those into the indexes, and then the rest of it will be put into the callback to be executed like a regular Boolean formula.
So actually at compile time, you hash all the keys and check how many additional lookups you have to do potentially?
Yeah, so in the strategy list, there's actually a parameter for the hash functions right here. And so here I'm saying don't do any additional probing. And here I'm saying look at the very next bucket to see if it's a hit or not.
But you know this at compile time?
I know this
looking
at
all
compile time. Yep.
Cool.
So I can benchmark all of these. I can sort them by performance, and then I just go through them one by one to pick the best one. Yeah.
Thank you very much, Luke. Unfortunately, we're running out of time, so I guess all pressuring questions have to remain for a future break, lunches, this evening's party, I reckon. Thank you very much for the talk again, Luke.
Thank you.